So today we're starting section 9.1, which is on something called polar coordinates. Okay, so this far in your math career, you have always plotted a point in terms of rectangular coordinates, x, y. So for example, here's our x-axis, here's our y-axis. We might have had a point that was 3, 2, and it looked something like this. This is called rectangular coordinates when we have things in terms of x, y. What we're going to do in this section is learn a new way to represent a point in space, and that's with something called polar coordinates. Okay, so this does relate to trigonometry once we get everything out here. So what we're going to do to represent this in terms of polar coordinates, okay, we're going to draw a ray from the origin through this point. And I'll write this all down for you. We're going to measure two things. We're going to measure, first, we'll call it R, the distance from the origin out to this point, we're going to call R. Now R usually stands for radius, so that makes sense. If we had a circle around the origin, that would be the radius. The second thing we're going to measure is the angle that this ray makes with the positive x-axis, and we'll call that theta. Okay, so what we can do instead of putting a point in terms of rectangular coordinates, x, y, we can put it in terms of what we call polar coordinates, and that is going to be r, theta. This is an R, not a V, sorry, R. Okay, so let's write out our official definition of polar coordinates here. It's a little bit long. We'll do a bunch of examples, and then it'll make sense. So if R is greater than 0, R is the distance of the point from the pole and we're going to use the origin as our pole. Theta is an angle formed by the polar axis and we're going to use the positive x-axis for our polar axis. And a ray through the point. A point in polar coordinates is written r, theta. I'll give you guys a second to jot that down. Okay, so if r is greater than 0, r is the distance of the point from the pole. We're going to call the origin the pole. Theta is an angle formed by the polar axis. We'll use the positive x-axis and a ray through the point. A point in polar coordinates is written r theta. It's always written in that specific order, r, theta, not the other way around. So not theta, r. Sort of like rectangular coordinates is always in the order x, y, not the other way around. Let me draw your attention to a couple things. We always measure the distance from what we call the pole out to the point. So we're going to use the origin, the distance from the origin out to the point. And then something else that's important is theta is an angle formed by the polar axis and a ray through the point, through. It's not the only angle. As we saw in previous sections, right, if this was a ray through a point, we could measure the angle in the positive direction. We can measure an angle in the negative direction. We could actually make 2 full revolutions and come back to this. So it turns out that there's actually an infinite number of ways to write theta. Usually we like to pick the theta between 0 and 2 pi. That makes the most sense in our real world, but just realize, and we'll do some examples like this, that there's more than one way of writing theta. So let's look at a picture. I already had a picture up there, but let's label some things out. Here's a point, r theta. Let me see if the green shows up better. So in order to write the point in terms of r theta, what we do is we draw a ray through the point. We measure the distance r from the pole out to the point, and then we measure theta from the polar axis out to the point. Now this works with a point in any of our 4 quadrants. So just for fun here, let me draw a point in the 3rd quadrant. What we would do is form a ray through that point, measure the distance r from our pole out to that point, and then our polar axis is always going to be our positive x-axis here. We would measure the angle theta between that polar axis and the pole. I'm sorry, the polar axis and a ray through the point. Again, this is not the only way of finding theta. We could actually measure around here, and we'll call this theta sub 2, another option for theta. Okay, so usually in your homework, it'll specify to leave theta between 0 and 2 pi. In the real world, it makes the most sense to not go negative and also not do a bunch of revolutions and come back to that. All right, any questions so far? Okay, so let's plot some points given to us in polar coordinates. Okay, so plot the points. Let's plot the points 2, pi over 4. Okay, so the first thing we're going to do is draw our angle. So even though this is in the order r theta, in order to plot this point, we need to put theta in first. Okay, so theta is pi over 4. So the very first thing we'll do is draw in pi over 4. So pi over 4 we know is 45 degrees. So here's pi over 4. Now to get to that point, r is our distance from the pole out on this ray to the point. Okay, so what we're going to do for our class is we're just going to draw some approximate pictures here. So I'm going to put my point and then draw a 2 in here to indicate that it's a distance of 2 away from the pole, which is the origin. Now, what you might see on your homework or in the textbook is concentric circles that will help you measure out. So on your homework, or if you ever have polar graphing paper, what it'll look like is concentric circles mean circles with the same center. So graphing paper for polar coordinates looks something like this. So what you would do is plot in the angle here, and then we want to go a distance of 2 out. So we would actually measure 1, 2, and this would be a distance of 2. Okay, so kind of like when we're plotting things in rectangular coordinates, we have graphing paper that looks like this. Polar graphing paper would look something like this. On your homework, most of these are multiple choice. You don't have to do these by hand, but I would get in the practice of just trying to do it by hand and then pick the multiple choice one on the MyMathLab homework system. All right, let's do a couple more. The next one, 350 degrees. Okay, the first thing we'll do is plot in our angle 150 degrees. So 150 degrees, we know that that is in the second quadrant and it's 30 before 180, so it's about right here. So here is 150 degrees. Okay, then to plot our point is a distance of 3 away from the pole, which is the origin. So again, we'll just do an approximate drawing here, and we'll label this with a 3 to indicate that's a distance of 3 away from the origin. the pole. Any questions on that? Okay, let's do a couple more. And if you were doing with these concentric circles and you wanted to count out 3, you would count 1, 2, 3. Okay, next one, let's do 2 comma pi over 2. So the first thing we want to do is draw on our angle. That's pi over 2, which is of course 90 degrees. And then we want to go a distance of 2 away from the pole, which is the origin. So here's 2. Here's our point. We put a 2 in here to indicate that that's the distance. Now, these are the polar coordinates. This point, this is easy enough to see what the rectangular coordinates are. Okay, so in rectangular coordinates, help me out with this one. This point, what's the x coordinate of this point? 0. What's the y coordinate of this point? 2. Okay. So this point can be written in 2 different ways. In polar coordinate, it's 2 comma pi over 2. In rectangular coordinates, it's 0 comma 2. And I forgot to label my angle in here. So what we're going to do later on in this section is we'll learn how to take these other points and convert them to rectangular coordinates, and we'll go back and forth in both directions between polar and rectangular. And of course, it all boils down to trigonometry. Any questions on this one? Okay, let's do 2 more. So let's do 5 comma 5 pi over 3. And then the last one here, we'll do 1.5 comma negative 50. Okay, so we'll do 2 more. Okay, so next one is 5 comma 5 pi over 3. So the first thing we want to do is draw in our angle. So thinking about this in terms of fractions, 5/3 is 1 2/3. So if it's 1 2/3, that makes it 1/3 or 60 degrees away from 360, right? So that's going to be right about here. The next thing we want to do is taking r, that tells us our distance from our pole out to our point. So we'll go a distance of 5 from our pole out to our point, and I'll just write a 5 here to indicate that that's how far we've traveled. That's what that distance is. Last one, 1.5 comma negative 50. First thing we'll do is draw a negative 50. So remember, when we draw an angle in the negative direction, we're going in the clockwise direction. That's a little bit bigger than 45, so it's going to be right about there. And we want to go a distance of 1.5 away. So I'll just put my point out here and I'll label this 1.5 to indicate we've traveled a distance of 1.5 from the pole out to that point. Any questions on plotting these points? Any questions? Okay, so going back to this last page, we had the beginning of our definition for polar coordinates was if r is greater than 0. Okay, so what we want to do now is talk about what if r is not greater than 0, what if r is negative? And this still should hopefully make sense to you if r is negative. So like on this one, we counted out positive 5. If instead we had negative 5, instead of going in this direction, we would go in the opposite direction. Okay, so let's write out what this looks like and we'll do some examples. If r is negative, the point is on the ray opposite of the terminal side of the angle. So if r is negative, the point is on the ray opposite of the terminal side of the angle. So let's plot -2 comma pi over 4. So what we want to do, the first step is to draw in our angle. So pi over 4, we know that's 45 degrees. Okay, so here's pi over 4. Okay, our goal is to plot this point. So we need to figure out where this point is. So if this was a +2, what we would do is go from the pole, go on this ray through, go a distance of 2, so 1, 2. But because this is -2, instead of going in this direction up the ray, what we want to do is go in the opposite direction. So what would be helpful to us is to form the opposite ray. Okay, so the opposite ray goes in the opposite direction. These two rays together form a straight line. Okay, so now what we're going to do is go a distance of 2 on this opposite ray. Distance we're always mark with a positive number. So the distance from the pole out to this point is +2. This point is the point -2 comma pi over 4. Let's do another one. How about -3 comma 2 pi over 3? The first thing we'll do is draw in our angle 2 pi over 3. We know that's 120. The next thing we want to do using r, we want to figure out where our point is. So if r was positive, we would go up this ray. Because r is negative, instead of going up this ray, what we want to do is go the opposite direction, go down the opposite ray. So it would be helpful to us to draw in the opposite ray. That is the ray that goes in the opposite direction. These two rays together form a flat line. So now down the opposite ray, we want to go a distance of 3. So we label this with a 3. So again, the distance we always label with a positive number. This negative indicates the direction we're moving. Instead of up this ray, we want to go down the opposite ray. Okay, so this distance should always get a positive number. The negative indicates the direction. Okay, so this down here, this is the point -3 comma 2 pi over 3. Any questions on this? Now, you might think from these last two examples that there's more than one way to write a point in polar coordinates. For example, if we wanted to write this point in a different set of polar coordinates, we could figure out what this angle is and have r be +2. So it turns out another way of writing this would be +2 comma 5 pi over 4. Okay? Another way of writing this point in polar coordinates, we could, using this picture, we could measure in the negative direction, and we could write it as 2 comma 3 pi over 4. Okay, so there's more than one way to write a point in polar coordinates. There's more than one way to write a point in polar coordinates. Turns out there's actually infinite number of ways to write a point in polar coordinates. Typically what you'll see on the homework, you'll be asked to write r positive, or greater than 0, and you'll be asked to write theta between 0 and 2 pi. Okay, so that's very typical because that makes sense in a real world situation, but you might see some things where you have other constraints. So let's look at a really simple example, and then we'll do one that's a little bit more complicated. So let's look at this point. This point is a distance of 1 away from the origin. So what we're going to do is we're going to come up with a few different ways of writing this in polar coordinates r theta. Okay, so the easiest one, if I just look at this angle right here, this angle happens to be what? What's this angle here? 0. Okay, so the first way of writing this point in polar coordinates r, the distance from the pole out to that point is 1. This angle is 0. Now, looking at this angle, what about if I drew it like this? Now, what's that angle? 360 or 2 pi. Okay, so I could also write this point as 1 comma 2 pi. I could also go around twice, and I could write this point as 1 comma 4 pi.
Will the homework and stuff tell us to write in degrees or radians?
Yeah, so the question was, will the homework specify to give your answer in degrees or radians? And absolutely. It kind of goes back and forth interchangeably between the problems. You'll see some in degrees and some in radians. How about let's think of another way we can write this point. Let me start over with a new picture of the same point, and we'll come up with some other ways we could write this. Okay, how about this? What if I draw this as my angle? Okay, help me out with this one in terms of radians. What is this blue angle? What's this blue angle? Pi, okay. So let's say I pick pi as my angle. So now if I pick pi as my angle, here's my ray through pi. How do I get backwards through this point? I need to let r be equal to what? -1. Okay. Another way we can write this point, we could go in the negative direction here, and we could write this as -1, negative pi. So my point here is that there's an infinite number of ways we can write a point in polar coordinates. Okay, so in order to not have this ambiguity, usually on your homework, you're going to see this. You're going to be asked to have r be greater than 0 and theta be between 0 and 2 pi, or if it's in degrees, 0 and 360 degrees. Any questions on this one? Okay, let's do another example where we do this, where it's more formal, like what you might see in your homework. Find other polar coordinates of 2 comma pi over 4. And we have a few different parts here. A, they say they want r to be greater than 0, and they want us to find theta between 2 pi and 4 pi. We'll do a part B. They want r to be greater than 0 and theta to be between -2 pi and 0. And then we'll do a part C here. All right, so part A, they're asking us to find other polar coordinates of 2 comma pi over 4. And in part A, they still want r to be positive, but they want our angle to be between 2 pi and 4 pi. So remember, 2 pi is 1 full revolution, 4 pi is 2 full revolutions. So we want to go at least 1 time around, but not 2 times around. So let's start by plotting this point, 2 comma pi over 4. So first thing we do is draw an angle pi over 4. 2 is our distance from our pole out to our point, so this has a distance of 2. Okay, so now what we're asked to do is rewrite this with theta between 2 pi and 4 pi. So if theta is greater than 2 pi, that means we want to make at least 1 full revolution, and we still need to come back up to this same ray. Okay, so we'll make 1 full revolution plus we'll go pi over 4 more. So we have 2 pi, there's our full revolution, plus pi over 4 more. So 2 pi in terms of fourths, that's 8/4. So that's 8 pi over 4 plus pi over 4. That gives us 9 pi over 4. So this green angle going 2 pi plus 1/4 more gives us 9 pi over 4. So the other way of writing this, r is still 2. Our angle is now 9 pi over 4. Okay, so these two polar coordinates both correspond to the same point drawn here. Okay, next up, they want us to still leave r positive, and they want our angle to be between -2 pi and 0. So they want us to have a negative angle. So let's draw a picture. So let's put our point back up, right? We're looking at pi over 4, comma 2, I'm sorry, 2 comma pi over 4. Okay, so now instead of measuring in the positive direction, they've asked us specifically to measure theta in the negative direction. So what we're gonna do is we still put our initial rate here on the positive x-axis, but now we wanna measure around in the negative direction. So in the negative direction here, we are 1/4 away from being to -2 pi. So 2 pi is 8/4. So if we're 1/4 away from that, this is going to be -7 pi over 4. Right? All the way around would be -8/4, and we're 1 away from that. So another way of writing this point would be 2 comma -7 pi over 4. So all we're doing is looking at different angles to get back to that same ray. Any questions on that? Okay, part C is a little bit trickier. Part C, they've asked us to have r be negative. And so our goal is to still get back out to the same point. So we'll start over with a new picture here. Okay, so our goal is to still get back out to the same point, but they want r to be negative. So if r is negative, that means this is not the terminal ray through our angle. This is the ray opposite to our terminal ray through the angle. So what we're going to do is draw in the opposite ray. Those two rays form a straight line. Okay, so what we want to do now is measure this angle in the positive direction, figure out what this angle is, and then figure out what r needs to be. Okay, so when we create these opposite rays, because this angle measurement in here is pi over 4, that means that this angle measurement in here is also pi over 4. Okay, so these opposite angles have to match. So this entire blue angle, we've gone pi plus pi over 4 more, so that's a total of 5 pi over 4 for theta. Okay, so our goal is to get back out to this angle. I'm sorry, get it back out to this point. So our angle is 5 pi over 4. So here's our ray through 5 pi over 4. Now, if we want to go in the opposite direction, a distance of 2, what do I need to let r be here? -2, yeah. Okay, so another way of writing this point is -2 comma 5 pi over 4. So the point of this exercise is that there's an infinite number of ways to write a point in polar coordinates. And what you want to be careful of on your homework, or if you see this in physics or engineering or any of your other classes, is what these constraints are, what they want you to have r be and what they want you to have theta be. It's very typical to always want r to be positive and theta to be between 0 and 2 pi, but you might see some instances in your other classes where you have some different constraints. Okay. Any questions on this example? Okay, so now what we're going to do is we'll work on converting polar coordinates to rectangular coordinates. And as we saw in some previous examples, some of them we can do visually, right? When we had that point that was on the y-axis, you guys could tell me what x and y was visually by looking at the picture. Sometimes we'll be able to do that. Sometimes we'll need to do some trigonometry, okay? So we're going to do this in 2 steps. First, we'll do in one direction. We'll go from polar coordinates to rectangular coordinates. And then we'll go in the opposite direction from rectangular coordinates to polar coordinates. If you have your calculator with you today and you want to pull it out to follow along with me, feel free to do so. Most of these problems in this section you should be able to do by hand, but of course, if you have access to a calculator for the exam, might as well get some practice with that now. So first we'll do converting polar coordinates to rectangular coordinates, and then we'll do the other direction. Okay, so we're starting with polar coordinates, so that's r comma theta, and our goal is to convert this to rectangular coordinates, that's x comma y. Okay, so what we're gonna do is together we'll come up with these formulas of how to do this, and then once we get the formula, I'll put it in a box for you and we'll write out what our formula is. But I do think that this one is very instructive, and once you see how to actually do these conversions, you don't have to memorize the formulas. All you have to do is draw one triangle. Okay, so the first thing we're gonna do is we're gonna draw a generic point. So here's a generic point. This distance from our pole out to our point is called r, and then this angle measurement is theta. Now, if I drop a perpendicular to the x-axis and I form a triangle, in terms of x and y, this side of the triangle is what? X or y? X. Okay, how about this side of the triangle? Y, yeah. Okay, so you don't have to memorize any of these formulas, and later on, if you're in calculus or calc 2 or calc 3 or physics and you need them, all you have to do is just draw a point, label r theta xy, and all the formulas will just unfold for you. Okay, so what our goal is we're starting with r theta, we want to end up with xy. So our goal is to end up with a formula that says x equals something in terms of r and theta, and y equals something in terms of r and theta. Okay, so let's start with x. We want to get a formula that has x equals something in terms of r and theta. So first thing I'm going to do is let's ignore y. So here's what we want. We want x is equal to something in terms of r and theta. So looking at this triangle, here's our reference angle. This side is what? Opposite, adjacent, or hypotenuse? Adjacent. This side is what? Opposite, adjacent, or hypotenuse? Okay, so we have adjacent and hypotenuse. So which trig expression should I use? Sine, cosine, or tangent? Cosine. Okay, so I have that cosine of theta is equal to adjacent, which is x, over the hypotenuse, which is r. Okay, we have one more step here. We multiply both sides by r. We get that x is equal to r cosine of theta. Here's our first formula. That was really easy, right? It didn't take us any work at all. So let's do the same thing for a formula that has y is equal to something. Okay, so let's block out this x. We don't want to use that right now. Okay, so we look at our triangle. We're ignoring this x. We want a formula that says y is equal to something in terms of r and theta. So this side y is what? Opposite, adjacent, or hypotenuse? Opposite. The side r is hypotenuse. Okay, so if we have opposite and hypotenuse, what trig expression should I use? Sine, cosine, or tangent? Sine, yeah. So we write down sine of theta is equal to the opposite y over the hypotenuse r. Last step, multiply both sides by r. We get y is equal to r sine of theta. So just like that in one step, we derived our formulas. If we start with r theta, we can plug them in here and get x. If we start with r theta, we can plug them in here and get y. Okay, so again, do you have to memorize these? Yes, you need to know them for the exam and for the final exam. However, all you have to do is draw this triangle, boom, you get these formulas. So let's write down our formal conversion here. If P is a point with polar coordinates r theta, then the rectangular coordinates of P, x comma y are given by x is equal to r cosine of theta and y is equal to r sine of theta. Okay, so you might be wondering, why would we want to convert between polar and rectangular coordinates? And when you get to Calc 2 and Calc 3, you'll do some integration where doing the integration over polar coordinates rather than rectangular coordinates actually makes it much simpler. So you'll do things like deriving the volume of a sphere by hand and coming up with that formula yourself. And usually when things are round or have a circle in them, turns out that if we use polar coordinates for limits of integration instead of rectangular coordinates, it makes it much, much simpler. Okay, so this being said, you might not see this for a couple classes, but it does actually make math simpler in some other situations. All right, any questions so far? Okay, so how else can you remember these? We've already seen this before, right? When when r was 1, if we were on that unit circle, x was cosine and y was sine, they go in alphabetical order. Okay, so we've already seen this before in other places in our class. Okay, so let's do, I have 3 examples of starting with polar and converting to rectangular, and then we'll do the opposite direction. Find the rectangular coordinates. Give the exact answer. Okay, so 6 comma pi over 6. So this is our r and this is our theta. Okay, so we'll use the formulas and then we'll also draw a picture to make sure that everything matches up. So the first thing we have is that to find x is equal to r cosine of theta. And to find y, we know that y is equal to r sine of theta. So all we need to do here is plug in r and plug in theta, plug in r and plug in theta, and then either work these out by hand or put them into our calculator. So here r is 6, so we have 6 times cosine of pi over 6. Here I have 6 times sine of pi over 6. Okay, if you have your calculator with me and you're following along, the first thing we notice is that our angle is in radians. Okay, so if you want to put this into your calculator, either you need to switch your calculator to radians or you need to convert this to degrees. Now, this problem asks us to give the exact answer. So some of you, your calculators are going to work for this, and some of you, they're not. Exact means not a decimal. It should be in terms of square roots still. So go ahead and try plugging both of these into your calculator. The other important thing is here you see pi. You need to actually use a pi button on your calculator. You can't type 3.14. That's not close enough. Okay, I'm going to work this out by hand. For those of you who don't have your calculators, or if you want to do this just for funsies, cosine of pi over 6 and sine of pi over 6. So let's draw pi over 6. We know that's 30. Our sides are 1, root 3, and 2. So I have 6 times cosine of pi over 6. So cosine is adjacent over hypotenuse. That's root 3 over 2. Sine of pi over 6, opposite over hypotenuse. That's 1/2. Okay, here the 6 and the 2 have a common factor of 2, so that reduces to 3 root 3. And here 6 times 1/2 is 3. Okay, because we're asked to give the exact answer, we need to make sure we have things in terms of this root 3. If your calculator gave you a decimal approximation here, you might have a way to switch. So Google how to convert between approximate and exact on a TI-30, and there might be a button to do it. Okay, so our rectangular coordinates, we got that x was 3 root 3, and we got that y was 3. Okay, so here's our solution. Now, what we want to do is draw a picture and make sure that everything matches up. Okay, so originally here, we had that theta was pi over 6. and that r was 6. What we just figured out was that x was 3√3 and that y was 3. Okay, so on our picture, we can check a couple things, especially if you're in an exam situation. You could check that Pythagorean theorem is true, right? 3 squared plus 3√3 squared is equal to 6 squared. You can check that. The easy things you should check are like scale, right? This is 3, this is like 5 point something, and this is 6. So yeah, that looks about right. The other thing we should check is that the x and y coordinates have the right positive and negative values, right? This point is in the first quadrant, so x and y should both be positive. So you can check those things just to make sure you're on the right track. Okay, our answer here, the rectangular coordinates, they need to be given as an ordered pair, x comma y. So if you were doing this on paper for a quiz or a test, you wouldn't just write these things. You need to make sure you write them as an ordered pair, x comma y. Any questions on this one? Okay, let's do, I got 2 more for you. Okay, so the next one, find the rectangular coordinates, and we're asked to round to 2 decimal places. So we want a decimal approximation. So we are asked to convert 2, 127 degrees. Okay, let's do this one backwards. I'll draw the picture first. Okay, you're welcome to draw the picture first or second. Here, I'll draw it first just so we can check that we're on the right track. Okay, so 127 degrees, let's draw that in. We know that is in our second quadrant here, something like this. And then 2 tells us our distance from our pole up to our point. So this is a distance of 2. Okay, drop a perpendicular here. What we're looking for is the x coordinate and the y coordinate. So looking at this picture, the first thing we know is that the x coordinate of this point, should be what? Positive or negative? The x coordinate here, positive or negative? Negative. How about the y coordinate here? Positive or negative? Positive. Okay, so there's going to be our first self-check. So let's do this now. We got x is equal to r cosine of theta, and y is equal to r sine of theta. Okay, so now what we want to do is plug in r and theta. So we have 2 cosine of 127 degrees and 2 sine of 127 degrees. Okay, this one we cannot do by hand, right? 127 degrees is not something we know how to evaluate by hand, so we need to go to our calculator. Okay, note that this is in degrees and not radians. So for the last problem, if you moved your calculators to radians, you need to move it back to degrees. Plugging this in your calculator, you should get negative 1.20. And here you should get positive 1.60. They asked us to round to 2 decimal places, so here I gave 2 decimal places. If we look at our picture here, let's make sure that this makes sense. You guys told me from the beginning that x was negative and y is positive, so that checks out. The next thing we could do is check Pythagorean theorem if we wanted to. 1.6 squared plus 1.2 squared is equal to 2 squared. Should be pretty close there. The other thing we can check is, of course, because it's a triangle, that the scale looks good. So we have sides that are 1.6, 1.2, and 2. Yeah, that looks right. Okay, so our rectangular coordinates here, x is negative 1.20 and y is 1.60. So our answer here, we need to write it as an ordered pair, negative 1.20, comma 1.60. Any questions on this? Okay, let's do one more. Find the rectangular coordinates, give the exact answer. And we're asked to convert 4, 3 pi over 2. Okay, let's draw our picture first again, just to see what we're up to. Our angle is 3 pi over 2, so we know that is 270 here. And we want to go a distance of 4 from our pole out to our point. All right, so without doing any work at all here, our goal is to come up with the rectangular coordinates. So the rectangular coordinates are x comma y. So looking at this point down here, what's the x coordinate of this point? 0. What's the y coordinate of this point? -4. Okay, so our rectangular coordinates are 0, -4. Now, let's say you didn't draw the picture or that wasn't super obvious to you, and your question was, can I still use the formulas? Absolutely. So let's write out our formulas. X is equal to r cosine of theta, and y is equal to r sine of theta. So here r was 4. And theta is 3 pi over 2. Okay, so here's where we go back to learning how to evaluate these quadrantal angles. So cosine of 3 pi over 2 is 0. So that gives us our 0. Sine of 3 pi over 2 is -1. That gives us our -4. Since you have your calculator out and you want to go ahead and try this in your calculator, you can type in 4 cosine of 3 pi over 2 and try 4 sine of 3 pi over 2. So again, we're back in radians, so make sure you have your calculator in radians, but you can get the 0 and the -4 from your calculator or by looking at this point visually. Any questions on this one? Any questions? All right. Anybody need more time on this page? Okay, the next thing we're going to do is we'll do conversions in the opposite direction. So on these problems, we started with polar coordinates and we converted to rectangular coordinates. Next, we'll go from rectangular to polar. And the process is a little bit different. Okay, converting rectangular coordinates to polar coordinates. So we're just going to start with rectangular coordinates x comma y. Our goal is to convert these to polar coordinates r comma theta. Okay, so what we'll do is we'll derive the formulas ourselves like we did in the previous directions, and then we'll write them all down formally here. Okay, so what we're going to do is start with a generic point, exactly like we did before. So here's a generic point. Here's r, here's theta. This side is x and this side is y. Okay, so now we're starting with x, y, and we want to get to r and theta. So our goal is to get a formula that says r is something in terms of x and y, and then theta is equal to something in terms of x and y. Okay, so first up, we want to come up with a formula that relates r with x and y. So let's block out theta. We don't want to use this in our formula, right? We just want r is equal to something in terms of x and y. So what formula here relates x, y, and r to each other? The three sides of a right triangle. What's that called? Pythagorean theorem. Okay, so we know x squared plus y squared is equal to r squared. So that means that r is equal to the square root of x squared plus y squared. And because we're taking r positive, we don't need to have plus or minus. We're just looking at the distance here. Okay, our next thing, we're starting with x and y, so let's cover up r here. We want to come up with a formula that relates theta with x and y. Okay, so looking at this triangle, here I have angle theta. Okay, help me out with this. These two sides in terms of opposite, adjacent, and hypotenuse. So here's theta. This side is what? Opposite, adjacent, or hypotenuse? How about this one? Opposite. So I have adjacent and opposite. So what trig expression, sine, cosine, or tangent, relates these two sides? Okay, so we have tangent of theta is equal to the opposite over the adjacent, which means that theta is equal to inverse tangent of y over x. And I'm going to put a little star by this because there's one little catch. So here are our two formulas. Now, why did I put a little star over there? Theta is equal to inverse tangent of y over x. So remember, by definition, when we do these inverse trig functions, they're only going to return angles in specific quadrants. So inverse tangent only returns an angle in quadrant 1 or quadrant 4. So this only works if our angle is in quadrant 1 or quadrant 4. Okay, so down here, I'm going to write the steps for doing the conversion, and we'll account for that. Okay, so our first step is we're going to plot the point xy. Our second step is if x equals 0 or y equals 0, we should just visually find our theta. Okay, if we can visually find r and theta, that's great. Why do I have to put this step specifically in here? The reason why I actually have to write this step specifically in here is because we cannot divide by 0, right? If we think about that graph of tangent, tangent isn't defined everywhere. So we have this problem where if x is 0 here, we actually can't use this formula because 0 is not allowed to be in the denominator. Okay, so sometimes these formulas don't work, but we could visually find these things. Okay, step 3, otherwise, we use our formula. So we'll find r first. We get that r is the square root of x squared plus y squared by Pythagorean theorem. Then we need to find theta. So if the point is in quadrant 1 or quadrant 4, then this works. Theta is equal to inverse tangent of y over x. But if the point is in quadrant 2 or quadrant 3, this formula, this inverse tangent, can only return something in quadrant 1 or quadrant 4. So what we're going to have to do is take this formula, and we're going to have to bump that angle over to quadrant 2 or quadrant 3. So if we're bumping it over by 2 quadrants, we're adding 180 degrees. Or if we're in terms of radians, we're going to add pi. And I'll show you in the examples why this works. Okay, so adding 180, adding pi, that bumps us from quadrant 1 or 4, it bumps us into the right quadrant. And then step 5, you should always check your answer visually and make sure that that makes sense. Okay, I'll give you guys a few more seconds to get this all copied down. All right, so let's do, I have 3 examples going from rectangular to polar coordinates here for you guys. Convert to polar coordinates. We're asked to give the exact answer. Write theta in radians. With theta between 0 and 2 pi. Okay, so we are going to convert 2, -2. So that's in rectangular coordinates. We want to convert this to polar coordinates. So in rectangular coordinates, this is x, y. So our step 1 was to plot our point. So here's 2, here's -2, here's our point. If x equals 0 or y equals 0, step 2 was to visually find r and theta. That's not the case. So our next step is to find what r and theta is. So let's draw our picture here of our angle. So here's r, our distance from our pole out to our point. This specifically says we want theta to be between 0 and 2 pi, so we're measuring in the positive direction. This is going to be theta. Now, some of these problems, you might actually be able to visually find both of these things because we know these two triangles, these 45, 45, 90, and these 30, 60, 90 triangles really well. Sometimes you might be able to identify these angles just from the picture. So if that's the case, you're welcome to use that as a shortcut or to self-check. I'm going to go ahead and use all the formulas, make sure everything looks right. Okay, so step 3 was that r is equal to the square root of x squared plus y squared. Okay, so we have the square root of 2 squared plus -2 squared. So 2 squared is 4, -2 squared is 4. So we have the square root of 8. We are asked to give the exact answer, so we need to simplify this. So 8 is 4 times 2, so this is 2 root 2. If you have your calculator out and you feel more comfortable on your calculator, go ahead and plug this in. What you want to check is whenever you're asked to give an exact answer, some calculators will do this for you and put it out in terms of root 2. Some calculators will give you the decimal approximation. So if you get the decimal approximation, but the problem asks you for the exact answer, you're going to need to do this by hand to get that exact answer. Or like I said, some calculators have the ability to go back and forth between exact and approximate. So Google that, how to switch between exact and approximate form on a TI-30X or whatever you might have. Any questions on how I got R? Okay, next step. Oh, we can look at our picture here. This should make sense. 2 root 2 looks good. Next step is to find theta. So theta, if the point is in quadrant 1 or quadrant 4, we're going to use inverse tangent of y over x. So we have inverse tangent of -2 over 2. All right, in your calculator, or you can do this one by hand if you'd like. Inverse tangent of -2 over 2. The first thing you want to make sure you do, anytime you use inverse sine, inverse cosine, or inverse tangent, okay, so anytime you put inverse sine, inverse cosine, or inverse tangent in your calculator, you should be in degrees. This is really, really, really important. If it's in radians, unless you have a super fancy calculator that spits out pi over 4, -pi over 4, you need to be in degrees. Okay, so just for fun, if you have your calculator out, go ahead and try inverse tangent of -1 in radians and try it in degrees. In degrees, you should get -45 degrees. If you're in radians, it's going to give you the equivalent of -pi over 4. Remember, pi is 3.14159 something. So if you're accidentally in radians, it's going to give you some crazy long non-terminating decimal that's really, really hard to identify as -pi over 4. Okay. So we're not done yet. Actually, any questions so far? Okay. So we're not done yet. What we want to do is let's see what our problem tells us. It specifically tells us that we want theta to be between 0 and 2 pi in radians. So -45 degrees. This tells us that this angle is -45 degrees. which is negative pi over 4. The problem asked us to do it in radians, and it wants theta to be between 0 and 2 pi. So we are actually looking for this positive blue angle. Because the problem specified, it wants us to give a positive answer. Okay, so all the way around here is 2 pi. We are pi over 4 away from being to 2 pi. So that makes this angle positive 7 pi over 4. So our answer is 2 root 2, comma, 7 pi over 4. When I give questions like this on a paper quiz or a paper exam, the biggest mistake I see is students forgetting to give the positive angle as the answer. Okay, so in general, when you're in physics engineering, things like that, we usually want theta to be between 0 and 2 pi. So take this last step. Any questions on this one? Any questions? Also, make sure you write your answer as an ordered pair, r comma theta, for your final answer. Okay, I got 2 more examples for you guys. And if it's not specified about r should always be positive. Okay, so if it's not specified, we should always have r positive. So if theta isn't specified, theta should always be between 0 and 2 pi. Okay, so we're asked to convert 0, negative 3 to polar coordinates. So here's x comma y. Okay, so step 1 was to plot our point x comma y. So let's start with that. So x is 0, y is negative 3. So here's our point. Okay, step 2, if x is 0 or y is 0, visually find r and theta. So we want to find 2 things. R is our distance from our pole out to this point, and theta is this angle. And again, the problem specifies they want theta to be measured in the positive direction. All right, so help me out with this one, guys. R, our distance from our pole out to this point. Remember, we're talking distance. What's the distance from the pole out to this point? What's the distance here? Positive 3, good. Theta, theta is this angle. So we want to think in terms of radians. So we know this is pi over 2, 2 pi over 2. So that makes this angle 3 pi over 2. Now, this one we have to do visually. If you try to use the formulas, because x is 0, when we did inverse tangent of y over x, we would have inverse tangent of negative 3 over 0. And we're not allowed to divide by 0, so you're going to get an error. Okay, calculator error, domain error. So sometimes you have to do this visually, and the formulas don't actually work here. If you wanted to find r with the formula, right, square root of x squared plus y squared, that part would work out just fine. Any questions on this one? Okay, let's do one more. Okay, so convert to polar coordinates, write theta in degrees with theta between 0 and 360, and we're starting with the point negative 1.3, comma, negative 2.1. Okay, so the first thing we should do is plot this point, x comma y, to see what's going on here. So this is our rectangular point, xy. So our x coordinate is negative 1.3. Our y coordinate is negative 2.1. So here's our point. negative 1.3 comma negative 2.1. In order to get this in polar coordinates, we're going to need two things. We're going to need r, the distance from our pole out to that point, and we're going to need theta, the angle measured in the positive direction, because this problem specifically told us they want theta to be between positive 0 and 360 degrees. Okay, our next step was if x was 0 or y was 0, then we visually find these things. That's not the case, so let's move right on. The next step was to find r. R is equal to the square root of x squared plus y squared. So we have square root of negative 1.3 squared plus negative 2.1 squared. This is one I would not like to do by hand. So in your calculator, go ahead and punch this in, square root of negative 1.3 squared plus negative 2.1 squared. If you're following along in your calculator, you need a couple things here. The first thing is you need to tell your calculator that this entire thing is under your square root. The second thing is to deal with these negatives, okay? First of all, we know a negative squared is a positive, so really we don't even have to type these in. If you do want to type them in, your negative button is different than your subtraction button. So your subtraction button is just a dash. The negative button might be a dash inside parentheses, or you might have a button that says plus slash minus to get the negative. You should get 2.47. Okay, so remember, if you need help with your calculator, come see me, send me an email, Google, visit the Math Center, but make sure you're comfortable using your calculator before the exam so that you can get the right answers. Looking at our picture, we should make sure that this makes sense. We got 2.47. That looks good, right? One side of our triangle is 1.3, one side's 2.1, our third side's 2.47. Looks good. Any questions so far? Okay, the next thing we want is theta. So we have that theta is equal to inverse tangent of y over x. Now, looking at our picture, inverse tangent only returns an angle in quadrant 1 or quadrant 4. Our angle is in quadrant 3. So anytime it's in 2 or 3, it's not in 1 or 4, what we're going to do is add 180 to this. Because we know that tangent is periodic with period 180, that means this bumps us over to the right quadrant, and this angle has the same tangent as 180 degrees before it, right? Tangent's periodic with period of pi or 180. All right, so here we go. We got inverse tangent of y, which is negative 2.1, over x, which is negative 1.3, plus 180. We'll do this in 2 steps. So the first thing I want you to make sure is that your calculator is in degrees. So in degrees, I want you to just type in this part, inverse tangent of, if your calculator automatically does not give parentheses, you need to have those in there. Okay, don't type in the plus 180 yet, just do this part and hit equals. You should get 58.24 degrees. Okay, so when you're doing these problems, look at where 58 degrees is. 58 degrees here is in the first quadrant. Our point is not in the first quadrant. So when you're doing these, visually check your answer. And when you see 58's over here, that should remind you, okay, I need to do one more thing. I need to add 180. So my actual angle is 238.24 degrees. Okay, so our answer, r comma theta, is 2.47 comma 238.24 degrees. Any questions on this? Any questions? Okay. The last thing I want to do in this section is talk about equations in polar form. So as I mentioned a little bit earlier, you might be wondering, like, why do we want things in polar coordinates rather than rectangular coordinates? And it turns out that once you get to calculus, polar coordinates will actually be much easier. Sometimes equations in polar form rather than rectangular form will also be much simpler. Okay, so I just have a couple of quick examples of looking at some equations in polar form. Okay, so first up, I have an equation. So 7x squared plus 7y squared is equal to 9. We are asked to write this in polar form. Okay, so in polar form, what I want to do is have it in terms of r and theta instead of x and y. So there are a couple tricks here. The first thing I see is x squared plus y squared. So we know that x squared plus y squared is equal to r squared. Okay, so what I'm going to do is start by just dividing everything through by 7. And I get x squared plus y squared is equal to 9/7. Okay, we know x squared plus y squared is equal to r squared. So I get r squared that is equal to 9/7. So what I've done in this example is I've started with something in rectangular form and I've written it in polar form. Okay, so instead of x and y, I have it in terms of r and theta. This one doesn't have any thetas, which is fine. Now, here's one place where polar form might be beneficial. Our original equation had 2 variables, x and y. In polar form, this only has 1 variable, r. So when you get to calculus, it is advantageous to have the least amount of variables. So this only has 1 variable, this has 2 variables. So this might be an example where if we want to integrate, if we put it in polar form, we only have 1 variable now. This actually simplifies the problem greatly. Any questions on that? Okay, we'll do a couple more. So same thing, write in polar form. And I'm starting with x squared is equal to 13y. Okay, so what I'm going to do is put this in terms of r and theta. So anytime I see an x squared plus y squared, we would want to replace that with an r squared. Here we don't have x squared plus y squared. Okay, so what we're going to do is just use those formulas we had for x and y. So we know that x is equal to r cosine of theta, and y is equal to r sine of theta. We'll work this out a little bit. So r cosine of theta squared, square the r. So I'm going to write that as r squared. And then cosine of theta squared, we write as cosine squared of theta. Over here, I have 13 r sine of theta. Sometimes in your homework, you'll be asked to put this in general form. In general form, we are asked to have 0 on one side of the equation. Okay, so anytime you're asked to write something in general form, what I want to do is take one more step here. And get 0 on one side. Okay, so this is called general form. Now this one, I would argue that putting this in polar form is not at all simpler than looking at it in rectangular form. Okay, so sometimes, like on this first example, polar form's a lot nicer. Here, I'd say equally as complicated. Oh, and let's backtrack. Shoot, I totally forgot. On this last example, if we look at either of these, if we were to draw these out, this is the equation of what shape? X squared plus y squared is equal to r squared. What's that a shape of? A circle, right? So this actually r squared, this just is the circle that has all points whose radius is square root of 9/7. Okay, so these are just equations of circles. All right, let's do one more. Any questions so far? Okay, let's do one more. Let's do the opposite direction. Let's write in rectangular form. Okay, so right in rectangular form, I'm going to have r is equal to 7 sine of theta. Okay, so this one requires a little bit of trick. So what I want to do is write this in terms of x and y. So looking at this and thinking about our formulas that we have between x, y, r, and theta, we don't see anything right off the bat that we can substitute in. So this one requires a trick. What I'm going to do is start by multiplying both sides of the equation by r. So now I get r squared is equal to 7r sine of theta. Okay, so now r squared we know is x squared plus y squared, and r sine of theta is equal to y. Okay, so sometimes we have to do things like this in order to get these equations in terms of things that are easily to substitute. So r squared is x squared plus y squared, and r sine of theta is equal to y. Okay, so now it's all in terms of x and y's. The last step we want to take here is to put it in general form. So putting this in general form, we want to get 0 on one side, and usually in general form, what we like to do is write our highest to lowest powers. So usually we put our terms with squares in them first, and then our terms with x and y to the first, and then our constant term. Okay, so general form means 0 on one side, and then highest to lowest powers on the other side. Okay, so if we look at these two equations, it might be beneficial to write it in rectangular form, right? If we're not comfortable in polar form, this r is equal to 7 sine of theta. If we were asked to graph this, this would be really tricky for us. Down here, we could graph this. This ends up being, I believe, an ellipse, right? We can work on that.